Hi all, Mr. Pope here, and we're going to be looking at some graphs in decision maths in the second session on the topic. Okay, so today we're mainly going to be looking at a lot of essentially definitions, right? Decision maths is going to be introducing a lot of topics that are just going to be, dependent on you knowing exactly what's going on. So let's just jump into it. So let's look at a graph. Okay, and I want to stress the context of, in mathematics, when we talk about graphs, we normally talk about the x and y Cartesian plane and functions going on like that. This is not what we're talking about this time. The context of the graph in this point has got fairly unique features, and essentially they're just they're diagrams to convey the idea of nodes or vertices, which are points essentially, or stations, and arcs or edges, which I'll denote with lines. So an example of a graph would be, I don't know, let's say the point A, and this is the point B. Let's say this is the point C, and this is the point D. Okay, now I can connect A to B like so, and B to C like so, and I could leave it like that. Now, this would be an example of a graph, that isn't connected. Okay, so this idea of connections, if all of the nodes can be reached in such a way. For example, if I'm at node D, there's no way for me to get to A, B or C. So we say that this graph isn't a connected graph. However, if I copy this and add a vertex, so let's say I then add a vertex like this, then we would say it is connected. At the moment, this is a connected graph. We can actually go one further and say that it's a simple connected graph. Okay, now what would be an example that's not simple? Okay, what would not be a simple graph? Well, if I take this again, then what am I not allowed to do? I'm not allowed to have multiple connections between 2 points. Okay, that's not cool. So there must always be one unique connection, in this case an edge, between vertices. And also what we're not allowing is a vertice to loop onto itself. So C going to C like that. This is called a loop. So we're not allowed to loop, and we have to have unique connections between the vertices or nodes. Okay, so that's a key concept there. So graphs that are not simple. This is a simple connected graph. This is not a connected graph. There's various other things. For example, I could make a subgraph of that thing. So for example, a subgraph could just be B to C, and it's just a collection of points. So it's just a collection of points, connections in the main graph. That's what a subgraph is. So a typical example there would be from B to C like that, because that is only a small portion of the graph. Okay, now before we move on, there's another little bit I want to talk about, and that is order or valency of nodes. And this is a really key concept, and it is essentially the number of edges, connections each node has. So let's go back to the example over here. So let's deal with this. So if I have the order, let's have A, B, C, D, the order of the valency of each node. Well, A has 2 edges sticking out of it, that's order of 2. D has only 1 edge sticking out of it, so that's 1. B has 2 edges, so that's 2. And C only has 1 edge popping out. Okay, so what does this mean? What's a consequence of this? So, a consequence. In any simple connected graph, the sum of the order of the nodes is always going to be even. So in this example, 2 plus 1 plus 2 plus 1 is 6. And this thing is called the hand shaking lemma. Okay. So, handshaking lemma, made famous by a guy called Euler. We'll be looking more at Euler in this chapter. In actual fact, one of the cycles, or trails, depends what you want to call it, is named after Euler. And why is it called the handshaking lemma? Well, because if I look at, say, A and B, for example, A and B are shaking hands, if you like. And from that connection to A to B, if I put it down here, if I look at the connection between A and B, then from A's perspective, this one singular arc has contributed 1 to the order of A and 1 to the order of B. By A and B shaking hands in that sense, then that arc has contributed 2. Okay, every single one of these red lines has contributed 2 orange arrows, haven't they? And in total, there's 6 orange arrows. I can't draw a red line and it only contribute 1. For example, that would just be a node and then a connection going off and not connecting to anything. And we're not allowed to have that. So it's always going to be an even number. Okay. So let's go over to a couple of other key points. Let's say we're going to define something called a walk. Okay, so here's my graph. So a walk is just a route on the graph without visiting a node more than once. So a really simple walk could be D, A, B. Dab. And we usually indicate that we're doing the walk by putting hyphens in between the letter. Okay. Right. Now, the difference between a walk and a trail is, well, a trail is the same thing, but it's a route on the graph, same as before, between the vertices, but this time no edge is visited, or is traversed, sorry, no edge is traversed more than once. I'm just trying to think what I can add to this diagram to make it work. Let's say I add a connection from D to B. Then a trail could be from C to B to A to D and then back to B again. Although I've visited B twice, this is still a trail because I have not traversed any of the edges more than once, because I've gone from C to B to A to D to B again. So I've actually used all of the arcs or edges once and only once, so that's a trail. Okay, and technically this isn't a walk, this is a path, and a walk is more general. A walk is just a route along any edges from one vertex to the next. So a walk in my previous example could have been A to B to C, back to B again, back to A. Now that wouldn't be a path because I've visited A and B twice, and that wouldn't be a trail because I've gone across the same arcs twice. Okay. What else have we got? Cycle. Yeah, no, that's important. Cycles. How am I going to fit this? So let's talk about cycles. Cycles, really, really important. And essentially a cycle is where we take a walk where the start and finish node are the same. So let's copy this down. Let's say I've got this node now. A new diagram, so I've got this like that. And there's multiple ways I could create a cycle from this. For example, I could just go A, B, C, D, back to A again. So it's just A, B, C, D, A again. That's totally fine. Another example could be A to C to B to D and back to A again. So I'm going A, C, B, D, A, like that. Again, that's also a valid cycle because I'm starting and finishing on the same node, which in this case is A. Now, there's two types of cycles that we're going to be looking at. Very important. One of them is called the Hamiltonian cycle, and the other one's an Eulerian cycle. Okay, so a Hamiltonian cycle is just a cycle that visits every node once, apart from obviously the start and finishing node. So in both of my cases, I've found a Hamiltonian cycle because I've gone along all of the... To be fair, when I did a cycle, I could have very easily given my cycle as A, B, C, A. I didn't have to traverse all the nodes. I could have gone A, B, C, A, and I've made a little cycle and I've started back on A. However, the Hamiltonian cycle is where I visit every node once. So that's a Hamiltonian, that's a Hamiltonian, because I've only visited every node once and only once. So that's a key point. However, an Eulerian cycle is a cycle that traverses every arc or edge once. And it also, well, yeah, it's a cycle, so it starts on, yeah, so it starts and finishes on the same node. So that's interesting. Is it possible for this to happen? I.e., can I visit every edge on this? Well, let's try it. 1, 2, 3. No, I'm stuck. I've missed out DC. What if I start down here? Nope, I'm stuck. And you could do this for a long, long time. Essentially, if I'd gotten rid of the middle two, then A, B, C, D, A again would be not only a Hamiltonian cycle, but also an Eulerian cycle, because I've travelled from I've touched every node and I've traversed every edge. Now you're probably thinking, okay, so what's the point? Okay, so how can I identify an Eulerian cycle? And that's easy. It's only possible if the order of every node is even. Okay, that's a natural consequence. So if we look back up at this diagram over here, because B and D had odd nodes, then this is not an Eulerian, this cannot be made into an Eulerian cycle. And then if we look at the simple square case down here, if I take these two out, then A has order 2, B has order 2, they all have order 2 by symmetry. So actually, yes, this can be made Eulerian. And there's a simple reason why. Well, let's take a reason. Let's say we've got a node, right? Let's say we've got the node here, right? Now, if I have got an even amount of arcs, let's say 2, let's suppose we started at this node. Then one of the arcs would be going away and another arc would be coming back in. Okay, now that's great because we want to finish on that node. So if we go out with one of the nodes, we do a bunch of stuff, and then we can use the last edge to come back in. But look what happens if it's an odd amount of arcs. Then we can have a third arc, which we need to traverse, but if we are going to, we're going to have to go away, so we're not going to end on the same node we started on. So we're going to need an even amount of nodes if that node originally wasn't the one we started on. Okay, so let's suppose it wasn't the one we started on, so it's just a random node. Okay, how does that help us? Well, if that's the case, then we must have come into that node from somewhere else because we started somewhere else, and then the even node will be going away, which we're going to need to because we can't finish on that node. But if we have an odd amount of nodes, that must mean we'd be sucked into that node. We'd go in, and there's no even node for us to go back out again. So the amount of order of a node has to be even for it to be an Eulerian cycle. And there's also this idea, it's a little bit beyond the course, but we might as well have it floating up here. There's an idea of what's called a semi-Eulerian cycle. And that is, you can add one vertice to make it Eulerian, and that is there is only one pair of odd order nodes. So if we look back up here, this is semi-Eulerian because I've got one pair of odd order nodes. So if I add a connection between B and D, which increases both of them by 1, so, oh geez, what am I on about? This was mental. Sorry. Lol. Oh, you silly boy. B is order 2, C is order 1, D is order 1. So I'd have to up the order of C and D because they're both odd. So connect C and D, so loop between them. And now you'll notice that I can actually make this a Eulerian cycle because I can go D, A, B, C back to D again, for example. Sorry, that was a massive error. Yeah, ignore that. That's the true errors here. Sorry, I was wobbling on for ages. But yeah, no, that's Eulerian cycles. You have to decide that are cycles that traverse every arc or edge once and only once. And the natural consequence is that all the nodes must have an even order or valency. A Hamiltonian cycle is one that visits every node once. A little bit harder to spot. Not impossible. Usually they are done by inspection. Okay, what else can we do? Yeah, we can talk about weighted graphs. So let's make this a little bit smaller. So, hold on, let's take cycles. Let's make that a bit smaller. Let's push it into here maybe. Okay, directed graphs. So, what do I mean by that? Not directed graph. Yeah, directed graphs. So, what is a directed graph? A directed graph is where not only are they connected, but the arcs have an orientation. So, what does that mean? It means that A to B exists, but B to A does not exist. In this case, if I'm pointing from A to B like that, it could mean that D to B exists, but B to D doesn't exist. If there's no arrow, that means you can go both ways. If there is an arrow, then yeah, you have to follow that. What about, you could also write this as a directional matrix. Let's say A, B, well, actually, hold on. That's before I get ahead of myself. Let's have a similar deal, but now this time let's look at a weighted graph, and this is essentially where each of the connections have a weight. What do I mean by that? Well, let's suppose A, B, C, D, although that's not a geographical representation, let's say they're all cities, and what I'm going to put is the time in hours it takes to drive between them. So let's say A to B is 2 hours, A to D is 3 hours, A to C is 4 hours, D to C is 2 hours, B to D is also 2 hours, and B to C is 3 hours. Okay, and notice the same restrictions apply as before. This is not only a weighted graph, but it's also a directed graph. And A to B takes 2 hours, and you can't go from B to A. I don't know, maybe it's a one-way system or motorway. I don't know, just whatever you want to context you want to put it in. So another way of representing this is with a graph, or with a table. I always forget the name of these things, an adjacency graph and adjacency table. There's only one name for it. If you see it in a question, it's pretty obvious what it is. And we can't go from A to A, or B to B, or C to C, or D to D. But now, from going from A to B, we put a 2 there. But from B to A, so this is the stuff from, and this columns are the 2. then from B to A we can't do. So that's also, we'll just put a dash there, can't be done. A to C is 4, and A to D is 3. B to A we can't do, B to C is 3, and B to D we can't do either. C to A is 4, C to B is 3, C to D is 2, D to A is 3, D to B is 2, and D to C is also 2. Okay, so yeah, we don't really work with these tables so much. It's just another way of representing this information. Yeah, this is called a distance matrix. Sorry, that's it. Distance matrix. And yeah, it's for in this case it's for a directed and weighted graph. And in actual fact, for all the stuff we're going to be going on in future, weighted graphs are probably the most useful in terms of how we get from different places, the weighting, the importance of stuff. So, you know, weighted graphs are probably the most important thing to take away from this. But general graph theory is pretty decent as well. What else can we talk about? Yes, we can talk about isomorphic graphs. Yes, boy. Let's do it in one word. Isomorphism. And that iso just means equal, and morph, I want to say Greek, is just for shape or body. These are just graphs that are the same thing. For example, if I was to write this, like this, say this is point A, B, C, and I put a D in the middle like that, and I have A to D, D to C, B to D, like that. This is exactly the same as the graph we've seen before. Okay, these two pictures are what we call, they are isomorphic, i.e. they're just different visual representations of the same thing that's going on. For example, A is connected to all three other points, B is connected to all three other points, and C is connected to all three other points. Okay, and just literally, it's just a different, when the same orientation, number, valency of nodes and connections are the same. So essentially, if it's the same graph, they've just drawn it differently, then those two graphs are isomorphic. They're equivalent graphs. Okay. The other thing I want to talk about is connected graphs. Not connected graphs, you silly boy. Complete graphs. Complete graphs. And essentially, we write them in Kn, where n is the amount of nodes all connected simply to each other. So in the example of K1, I just have a single node. It's just connected to itself. We'll call it A. In the example K2, I've got two nodes, A and B, and I just have them connected simply, and now every node is connected to every other node. If I have K3, then I have three nodes, 1, 2, 3, A, B, C, and they're all connected to each other. A is connected to C and B, B is connected to A and C, and of course C is connected to A and B. So that's a complete graph. And then the K4 graph you've seen before, which is that. Now, for K5 and beyond, they're really easy to draw. What you do is you draw a regular polygon, of that many sides. So K5 would indicate a pentagon, A, B, C, D, E. And then the first thing you would do is you would connect around the edge, like so. And then you just connect every other node to every other node, like so. Now that is the complete graph for K5. Okay. Right, so is there anything else? Well, there probably is. I mean, there's so many definitions, and we'll pick them up as we go along. I think the last thing I want to leave you with is this sense of planarity. Okay, planarity, and a graph is planar when no vertices overlap, not vertices, when no arcs overlap each other. So, for example, this at the moment is not a planar graph. However, we can actually make this a planar graph by detaching one of the arcs and reattaching it so it does the same thing, like this. Whoops, let's make it a bit thinner. Like this. Now this graph is isomorphic to the graph I previously drew. So in this case, this is the planar representation of the graph we've been doing before. And checking to see whether graphs are planar is useful. There's various ways of making a planar graph look planar. The planarity algorithm essentially states that you find, so let's write it down. So the planarity algorithm. So step one is you find a Hamiltonian cycle and use that to create a n-gon. Create an n-gon. So if I look at this diagram here, well, actually, let's use the isomorphic case. So let's say I had this to begin with. Let's say, well, okay, let's try well, at the moment this is already an n-gon because the Hamiltonian cycle would be A, B, C, D. I've visited every node once and only once, and the n-gon it would create, because there's 4 nodes, would just be a square. So I've laid them all out, and then you'd represent the rest of it. So essentially step 1 is skipped in this bit. But other times you might have graphs where they're all over the place and things are going on. Then what you would do is you would list all the edges inside the n-gon. So the only 2 edges would be A to C and B to D. You would label one with I, for example. So we'd call it AC, we'd call it I. And then what we do is we check to see edges that overlap this newly labeled arc. And now, if they are unlabeled, then there's 2 things that can happen. Either those unlabeled arcs intersect each other as well as that new arc, and in which case the graph is non-planar, i.e. there's nothing we can do about it, it can never be planar. And if they don't, if no other intersections, then you label them O for outside, and then you repeat this process. Go back to step 2. So in our example, AC we label I, and the only thing that's intersecting A to C is BD. Now because BD, there are no other arcs inside this, so BD can't cross over with any other arcs, then BD will just be labelled O for outside. And now all the arcs are labelled, so we're done. And now all the arcs that have got I, we'd keep inside, and all the arcs that we label O, we put outside. So just like I did in this diagram over here. Okay, right, now there's loads to do with this. I'll go through a few examples. And yeah, let's give it a go. So same deal. If you want to pause the video and give it yourself here, give yourself a go, be my guest. Okay, so 2 graphs A and B are shown below. Write down an example of a cycle on graph A. Well, that would be easy. That could just be R to N to P to S back to R again. So we've got this as a cycle because it starts and finishes in the same node. We don't go along the same arc or node twice, it's just a cycle. Okay, why is U, Y, V, Z, Y, X not a path? Well, a path can't visit the same node twice, and I believe we visited Y twice here. So can't visit the same node twice on a path. Is that right? Let's have a look up here. Path. Route on the graph visiting a node without visiting node more than once. Yeah, I was right. Okay, how many arcs would there be? Oh, spanning trees. Okay, cool. Let's back up a bit. So what is a spanning tree? So a spanning tree, let's make this a bit smaller. So what is a spanning tree? So a spanning tree, so a spanning tree is just a subgraph of all the nodes, but vertices, just enough vertices, but just enough vertices to make the graph connected. So for example, a spanning tree of A, B, C, D could just be this. A, B, C and D are all connected. All the arcs are not present, but there's just enough arcs for them to be present. Okay, so when it says how many arcs would there be need for a spanning tree of A, well, let's think about it. There's 1, 2, 3, 4, 5, 6 nodes. Okay, so let's suppose we build up that tree. Well, if we start at R, we have no vertices. But then if we go to N, that's 1, 2, 3, 4, 5. And if you think about it, every time I add a node to my minimum spanning tree, I have to add a connector to it. So apart from the original node, every other node is going to have a vertex, is going to have an arc, sorry. So it's the number of vertices minus 1. So if there's 6 vertices, then there's going to be 5 arcs needed. For each graph, state whether it is Eulerian, semi-Eulerian, or neither. Okay. So, if it's Eulerian, then all of the vertices must have even valency. Well, I can tell straight away that N, Q, U, Z, they're all odd. So none of them are Eulerian, but they might be semi-Eulerian. Okay, well, let's have a look. Well, this has 3, this has 3, this has 3, this has 5, this has 2, this has 2. Again, the sum of all of these vertices is an even number, but unfortunately there's 1, 2, 3, 4 odd vertices there, so this is not semi-Eulerian. If we look over to the graph B, U has got 3, V has got order 4, W is 2, Z is 3, Y has got 4, and X is 2. So actually, because this only has 2 odd valency nodes, then actually A is neither, but B is semi-Eulerian. Okay, the graph shows designs to be etched on metal plates. The etching tool is positioned at a starting point that follows a route without repeating any arcs. Sorry, I'm just rubbing things out. Okay, the graph shows designs to be etched on metal plates. The etching tool is positioned at a starting point that follows a route without repeating any arcs. It may be lifted off and positioned at a new starting point. What is the smallest number of times that the etching tool must be positioned, including the initial position, to draw each graph? Right. Okay, so this one, graph A, is not Eulerian or semi-Eulerian. Okay, let's have a look at the semi-Eulerian first. Right, so where were the two odd ones? It was U and Z. So we could make this Eulerian by going from U to Z. Okay, so is it possible to travel across all the arcs and go back to the original place? Well, yes, it should be, because I should be able to go U, X, Y, U, V, dish, dish, dish. So actually, because the graph B is semi-Eulerian, so graph B doesn't need to be positioned any times, because it doesn't necessarily have to finish on the same node. If the etching tool, yeah. Whereas if I look at graph A, well, there's a couple of, let's look at the odd, because it's the odd vertices that are going to be a problem. So there's 3 here, there's 3 there, there's 5 here, and there's 3 there. Okay. Well, put it this way, what can we do? Well, when we have to reposition the blade, essentially what we're doing is we're saying ignore an arc. So if we say ignore P to Q, then that drops P to 2 and Q to 2 as well. And now actually this becomes semi-Eulerian, because now say we start at N, we can go something like this and finish at S, for example, and then we pick it up once and only once and put it at Q and then move it to P. So actually for graph A, we'd have to position once. Okay, an arc is drawn connecting Q to U. Okay, so, well, they're becoming super big arcs now. Okay, fine. Okay, so an arc is drawn from Q to U, like so. Okay, so the two graphs become one. The resulting graph is not Eulerian. Probably could have guessed that, but okay. Extra arcs are then added to make it an Eulerian graph. What is the smallest number of extra arcs are needed? Okay, let's have a look. Well, there's 3 here, There's 3 there. Q becomes order 4, U becomes order 4, V is order 4, W is 2, Z is 3, Y is 4, X is 2, T is 2, S is 5, and R is 2. Okay, where are the pickles? Well, it's N, P, Z, and S. So there's 4 odd graphs. So if we add another arc between 2 odd ones, then that will make both of them even. So we have to do that twice. The minimum could be from N to P again and from S to Z. That will increase all of N, P, S and Z by 1, which will make them all even, which will make them Eulerian. So what is the smallest number of extra arcs needed? The answer is 2. And the reason for it is because the valency of all the other nodes are already even, so it's just N, P, S and Z that need to be sorted out. Okay. Right. The graph's K5s has 5 nodes, A, B, C, D, E, and there is an arc joining every node to every other node. Yep, that's what complete graphs are. Draw the graph K5 and state how you know it's Eulerian. Right, so K5. K5, there's A, B, C, D, E. I'm drawing it as an irregular n-gon. And they're all connected, so stuff like this, so dosh, 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 there it is. And the valency of this, A, B, C, D, E, well, the valency at A is 4. By symmetry, they're all 4 as well. So because all nodes are even valency or order, that must mean it's an Eulerian, or it's just Eulerian. So this is part I. Part II, by listing the arcs involved, give an example of a path in K5. Your path must include more than one arc. Okay, well, a path is just where I don't repeat nodes, so okay, well, let's just go A to B to C. That's a bit silly. It's only 1 mark, but that's technically a path. Let's just double check with the definitions. It's a route on the graph without visiting a node more than once. Lol, yeah, that's it, just A, B and C. Okay, part 3, by listing the arcs involved, give an example of a cycle in K5. Okay, so a cycle could be A to B, and then B to C, and then C to D, and then D to E, and then back E to A, because that will just be, well, what is a cycle? That's what I've said before. Where is it? It's a walk, where a walk is your routes along edges from one vertex to the next, and it starts and finishes on the same node. So here the cycle would be A, B, C, D, E, and the edges I've used in the particular order is AB, then BC, then CD, then DE, then EA. Yeah, that's fairly straightforward. And that's it. That's all I've got. So there you go. Lots of definitions there. Hopefully I wasn't too confusing. But yeah, have a go at the exercises. The decision chapter is fairly easy. And yeah, have fun.